Hello and welcome to this presentation called Bearings in 25 Animations or Less. We'll be talking about rolling element bearings and fluid film bearings. My name is Jason Tranter, the founder and CEO of Mobius Institute. Okay, so let's first talk about detecting rolling element bearing faults. Fortunately, rolling element bearings give us a lot of warning of problems that they are experiencing. There's a lot of different ways we can cause the bearings to fail. There are a lot of different signs they can give us that there is a problem. It just depends whether it's EDM, like current flowing through the bearing, or there's a crack, or there's a lubrication problem, or there's a spall, or one of a number of different types of faults that can develop. But the fact is that as the balls roll along, or as the rollers roll through the bearing, we first detect high frequency vibration, and we can see both from the time waveform derived from that high frequency vibration or from a spectrum derived from the high frequency vibration, we can get a very early warning. As the fault gets worse, we can see changes in acceleration spectra and time waveforms, and then velocity spectra and time waveforms. So we get a lot of warning, and we can see how that fault develops. So let's just have a look at the patterns themselves. So what this little simulator is showing us is that as the balls roll along, so there's our balls going along, let's just assume for a moment that we have a fault right here on the bearing, on the outer race. So basically, any time that crack or spall or whatever it is, when that is between the rolling elements, there is no unique vibration. In fact, if the bearing was in perfect condition and the rollers were just rolling along, we don't expect to detect any unique vibration based on the bearings themselves. We'll get the 1x vibration, that's just the normal running speed vibration, which is the big sine wave we can see, but no other type of vibration should be seen from the bearing. But if we have a fault, for example, on the outer race, then every time one of these rolling elements strikes that point there, we get a little spike of vibration. Now, even though in my simulator there I show that spike, fairly large on the time waveform, in reality, in the very earliest stages of damage to the bearing, we can't see that on the time waveform. It's just too small. It's very low amplitude. But fortunately, it actually also generates very high frequency vibration as well. Imagine it's kind of like ringing a dinner bell, just ringing a tuning fork or something. We've got a periodic ping, ping. Hopefully when you heard my voice, it's when the rolling element was striking the red ball, red mark there, but it's kind of like ringing the tuning fork. So we can pick that up as a periodic source of vibration. We can detect that with certain techniques. I'll just explain a bit more in a moment. But anyway, that's a periodic vibration. Now, if the fault was instead on the inner race, as it was in the animation just a moment ago, as that damaged area rolls along with the shaft, we get a ping when it strikes that bearing, ping when it strikes that bearing, and so on. And therefore now what we are seeing is more frequent pings of vibration. In fact, if we go back to this animation, you can see it there. That white wave you see rushing out is the ping that I'm talking about. It's a stress wave which ripples out, or also called a shock pulse that ripples out. And we want to detect that. But as the fault develops, we will also detect it as normal periodic vibration in a spectrum or a time waveform. So that's another sort of fault, and then we can see if it was on the rolling element itself, then potentially 2 times per revolution of the rolling element, the damaged area will impact the inner race and outer race. Impact the inner race, then outer race, and we will see that in the time waveform as well. Now, if it's a ball and it's rolling along, it may be that it doesn't impact the raceway every time, or twice per revolution. If it's a rolling element, a roller, and then it's more likely that we'll see that vibration. But the key is that as the fault develops, it starts off being very small and the vibration grows and grows and grows. And if we use special techniques that isolate just the impacts themselves, it's called enveloping or demodulation. And then there's techniques like peak view and shock pulse and so on that specifically are designed to detect this type of fault condition. They specifically look for the high frequency vibration, they isolate that with filters and so on, they use rectification and all these sorts of things we don't really need to talk about right now. The point is they work, and if we get a fault on the outer race of the bearing, which is more common, then as each rolling element hits it, we get a certain ping of vibration, and we can detect that in the high frequencies. If on the other hand it's on the inner race, then we see something interesting happening here. We get the periodic ping, but you notice that the vibration level rises and falls, rises and falls, and that is a periodic increase and decrease in the amplitude of that vibration. That's because when the fault on the inner race is rolling over the top of the bearing, assuming the machine's mounted horizontally, there is less force in that impact as compared to when it's down below. Now that's all a lot of detail. The beauty of it is that if we see a pattern like that in our time waveform, or if we see a spectrum with sidebands, and I'll show you some in just a moment, then we can tell, okay, the fault's on the inner race. If on the other hand it's on the rolling element itself, then we get a much lower rise and fall of vibration. Let's just do that for a moment. Anyway, we see a rise and fall in vibration. It's just that it's a lower frequency of modulation. Anyway, I've got some slides on that in just a second. So the beauty of it is I can detect it at different stages. One of the things, now this little simulator is a little bit complicated, but the thing is that as the fault develops, we see fault condition develop by monitoring the very high frequencies, and as the fault continues, it gets, as the fault gets worse and worse, the frequencies generated become lower and lower. So in the very early stages, we're seeing very high frequency vibration. So the enveloping techniques and the peak views and shock pulses and so on detect that. But notice in the normal spectrum, we're really not seeing anything. Really not seeing very much at all. But as the fault develops, if you continue to monitor it, you might notice that you'll see some of this higher frequency vibration get into the lower frequencies. And in fact, if you use enveloping techniques that filter both at the higher frequencies and at the lower frequencies, you'll notice that the higher frequencies will be increase in amplitude first, and then the lower frequencies. But then as we go further, the acceleration, which is more sensitive to higher frequencies, will begin to change. And we can see it in the time waveform and spectrum, and we go further, and our traditional peaks in the spectrum that I'll just explain a little bit more about in just a moment will start to develop as well. So the beauty of all of this is that it enables us to get an estimate or an assessment or an approximation of how long the bearing has to live. If we're just detecting these very, very high frequencies, we say, great, we can start thinking about the bearing we may need to order, and we can look forward to downtime that we have where we could replace that bearing, but we don't need to do it now. But when this fault gets quite bad, and there's a lot more noise and there's no high frequencies, and in fact it starts to look like looseness, now you have to act quickly. So bottom line is that these enveloping and peak view and shock pulse and these sorts of methods all give us a nice early warning. But notice the earliest warning we can get is actually when we detect the root causes of failure. It's really important to understand the root causes, like poor lubrication, contamination of the lubricant, excess load from unbalanced misalignment, resonance, and so on, and poor installation practices, the bearing being damaged when it's installed, cocked on the shaft, and so on. But this will give us the earliest warning. Using acceleration and either looking at the spectrum or particularly the waveform, we'll get a warning of the fault either later if we're not using this technique or as the fault gets worse, and then we can look in velocity, and last of all we can look at the overall level, sort of the typical sort of RMS reading where it's just one number. Okay, so that gives us an idea. Now, I mentioned some of this already, but just to say that first there's a fault on the outer race. We will see a frequency that we call the ball pass outer race frequency. That's BPFO, and we'll see a certain type of pattern. We expect when the inner race is turning that there will be vibration, there will be harmonics. So we expect to see a peak at that frequency and twice that frequency, 3 times and 4 times. This is whether we're looking at a classical sort of velocity spectrum or an acceleration spectrum or a spectrum of the enveloped signal itself, be it peak, view, shock, pulse, or whatever. It's only a question of exactly what sort of shape it takes and whether we expect to see 1x and other kinds of peaks there as well. But the point is we will see this peak and we'll see harmonics. It's non-synchronous, which means that this frequency is not an exact multiple of the running speed of the machine. So it might be 3.09 times or 6.7 times or whatever. It will be a non-integer number. There will be harmonics, so there's multiples, and under normal circumstances we don't expect to see sidebands. Okay, if it's on the inner race, then we again expect to see harmonics. We again expect it to be non-synchronous, but now we will see sidebands. So now we've got these 1x sidebands on either side. So there'll be little peaks on either side separated by the running speed of the machine. Now, the cage frequency is and sometimes called the fundamental train frequency, is the frequency related to just the turning of the cage within the bearing. If you see a peak at that frequency, which is normally just less than half the running speed, you need to take urgent action. But the other reason for saying it is that if we see damage on the rolling elements themselves, then again we see harmonics. Again, they're non-synchronous. It's a different frequency to BPFO and BPFI, but now the sidebands are of the fundamental train frequency, or that cage frequency. Okay, so moving right along. Now we'll just have a quick chat about the fluid film bearing vibration analysis. Obviously, fluid film bearings are also critical, like rolling element bearings. We need the rolling element bearings to keep on turning and providing great reliability. Same with fluid film bearings. However, a lot of our really critical machines, like the steam and gas turbines and major pumps and major compressors and so on, typically use these fluid film bearings, so it becomes even more important that we monitor them correctly. So, a few things. We can't use the same techniques that we've just used for rolling element bearings for 2 reasons. Number one, we can't rely on using accelerometers on those sorts of bearings. The thing is that and you'll see an animation in just a minute, right now. So inside the journal bearing, so here's the bearing and there's the journal, or it's a fluid film bearing because there's a film of fluid, the oil, that separates the journal, or let's just call it the shaft, and the bearing. So it's like what I'm trying to show in this animation. It's as if it's riding on this wave of oil. I'm exaggerating the motion as I do in all the animations, but it's riding on this film. Now, it means that this vibration is being cushioned And therefore, if we have an accelerometer sitting up on the bearing housing somewhere, we would be expecting this vibration, this motion, to be sort of transmitted through up to where the sensor is located. And this film of fluid, this little wave under there, really deadens that vibration. We may not see very much at all. So we can't rely on that technique. And the other thing is too, we're not usually looking for impacts. If we're seeing impacts, then something pretty serious is going on. But we are interested in the health of the bearing itself. You know, if there were rubs or something like that going on, well, we're interested in that. But we are also interested, or particularly interested, in the stability of this system. So, you know, the idea is this shaft's turning around and it's sitting nicely on this film of oil. It's supposed to be in a certain location within the bearing. For example, the shaft turning in this direction, it's supposed to be just off center to the right and sort of sitting in this area. It's a bit hard to see from that animation because I've exaggerated the motion so much, but that's what it does when it's stable. It can become unstable, and that can damage the bearing or damage the machine. And they are conditions called oil whirl and oil whip. So we want to monitor the vibration and the position of the shaft within the bearing to detect whether this is a problem now or could become a problem. We are also interested in other conditions of the machine, like unbalance, misalignment, preload, and other conditions. So that, you know, we are looking for the vibration that tells us about the health of the machine as a whole, but also of the bearings. Now we are also interested in, let's just call them the dynamics of the rotor dynamics. With a lot of these sorts of machines, the machine might operate above the critical speed of the rotor. That is, that as the machine's running up to speed, the shaft will begin to flex, kind of like a guitar string, you know, strums back and forward. It's resonating. The shaft itself is resonating, and the machine operates higher than that speed. So as it runs up, we are very interested in how it's operating as it goes through that speed. Anyway, so back to this animation. There's a few things I'm trying to show here. Number one, yep, there's our little wave of oil that the journal is riding on. But in order to measure this vibration, we use these two proximity probes. This probe can measure the distance between the tip of the probe and this surface. Now again, this is all exaggerated. The clearances are much greater and the motion's much greater than in real life. But basically, it can measure the distance and this one can measure the difference. So it's kind of like triangulation. If we can know this distance and this distance, then I can tell from moment to moment, or the system can tell exactly how it's moving. So in this case, I'm showing a little orbit here. I'll explain that in just a moment. But it is moving in this circular, actually elliptical motion, and these two probes can tell us that because they're constantly measuring how that distance is changing. It's kind of like triangulation. In essence, it's telling us how the center of the shaft is moving. Now, at the same time, we need timing information for the sake of the orbit and for phase, and that's what this probe, the key phaser, that's what it's doing. It's seeing the key way as it rotates around. Now they're not all in the same plane, so let's have a look at that. Okay, now it's rotating in the opposite direction, sorry for the confusion, but in any case, so now you can see that this probe is mounted axially in a different location to these probes. So here, typically mounted near the bearing, they are watching how the shaft is moving. So we've got an idea of what's happening in the bearing, and we'll have these probes, X or Y and X probes on each bearing, and then we might have just one key phaser looking at this. Now, in reality, there might be multiple key phaser probes for redundancy and so on, but that's another story. Okay, so even though this motion is greatly exaggerated, but as the machine's vibrating, if there's any amount of unbalance, anything, then the shaft moves. It moves in that circular motion. It's just exaggerated in this case. Well, those two probes let us measure how the shaft is moving, and we can plot that on a graph, and that's our orbit plot. What this animation is showing is that potentially I could measure at other locations, and I can see how the shaft itself is moving, whether it's moving in this circular motion here, where the center of the shaft is moving more than the ends. Now, in reality, I'm only going to have probes at the bearings, so it may be difficult to tell exactly what it's doing. But in any case, just for artistic license, this is how the shaft may be rotating as it goes through its first critical, and we'd like to have an idea of what motion exists. And that brings us to the orbit plot. So here is the shaft. Imagine I'm looking along it axially, and what I'm going to do is just slow down the motion a little bit and turn on the prox probes and the key phaser. So the probes could be mounted in this classical X and Y location, or they may be located here. It could be different configurations, and here we have the key phaser, and again it could be mounted just about anywhere. You need to know where the probes are mounted though, of course. But basically, as the shaft turns, the key phaser sees the key way, or maybe a key in actual fact. The two probes monitor the gap, which again is very exaggerated, but we end up with two sine waves from one from each probe, and we can plot them against each other. So X versus Y gives us this orbit, and we might find that, for example, there's more motion in the X-axis, and it wouldn't be exact sort of phase relationship, as in wouldn't be exactly 90 degrees phase, and we might see a bit of an elliptical motion. There's more movement, let's say horizontally versus vertically, bit of a phase relationship there, and we might see elliptical motion. There's so much more we could tell you about these orbit plots and exactly how they work. We're just trying to keep this webinar shorter to give you a taste of all of this, and hopefully tell you something that you weren't clear about before. Okay, so what we've learned so far is how the shaft moves as it rotates, and it's moving in this elliptical motion as we just saw, and that is what the center of the shaft is doing. That's the way to think about it. What's the shaft doing? So here it is. Now we've got it rotating counterclockwise, and if you imagine a great big shaft with an crosshair in the middle, that's what the orbit's showing us. How is the center of the shaft moving? So what is that orbit telling us? Well, let's sort of zoom out a little bit. There's our shaft. The center of the shaft is moving in that elliptical motion, so that's great. So that tells us that. What it does not tell us is where inside the bearing it's doing that. So there's our bearing, and right now I've got that more or less sitting right in the center of the bearing. It's moving in that elliptical motion. Now it just so happens that if I knew that was actually happening, I might be a little concerned, because it shouldn't be there. It should be down in this quadrant here for a shaft rotating in a counterclockwise motion like that. The bearing has a certain amount of clearance. The shaft can't, or the journal can't move outside that bearing, and we represent that available clearance by this circle here. And what we're building up here is a plot that gives you an indication of where the center of the shaft is located within the bearing. And this plot is called a centerline plot. So it's like the center of the bearing. Where is it within the bearing? So if we click one more time, you can imagine that there was our motion just before, but it should be, the center of the shaft should be rotating around a point in this quadrant, not in this quadrant, and certainly not up here. Now, if you look closely, as I attempt to drag the center outside of that yellow circle, it won't go because it's bumping up against the edge of the bearing. And as I move it around, that's the available clearance within the bearing. The bearing could be more elliptical in shape. There's different sorts of bearings we might have, but to keep it simple, there it is. And when it's rotating and moving in a sort of an orbital motion like that, or elliptical motion there, we are very interested in whether it's doing it here or over here or up there. That tells us something about the stability. The shape of the orbit tells us about the fault condition. If it's highly elliptical, it might mean that there's some preload. If it's very round and quite large, there might be some unbalance. And there's lots of other fault conditions that we can detect by the shape of the orbit, and the position of that orbit, if you like, within the bearing tells us about the stability of the bearing. Look, there's so much more we can learn about all of this. We can look at the response of the machine, we can look at a full spectrum, we can look at the response, we can see what happens as it runs through the critical speed. There's so much more we can learn, but the orbit tells us an awful lot, and from the X and Y waveform we can build a spectrum, we can build the magnitude and phase, we can build something called the full spectrum. There's a lot we can do to tell us all about the machine. Now, just want to tell you about a couple of things coming up. We have Category 4 vibration courses that really dive very deeply into all the topics we were just talking about. That's the journal bearings, rotor dynamics, orbit plots, and all of that. That is discussed in great detail in a Category 4 course, and we have one coming up in Dubai, as you can see with these dates. Special course for what I like to call the superheroes of vibration, the people that really get into the turbo machinery and rotor dynamics, but also modal analysis, learning about isolation, mass stiffness damping. It's like a very advanced Cat 3, if you like. It's all the things we learn in Cat 3, but more advanced, and the rotor dynamics as well. But what I also want to tell you about are the conferences we have coming up. We have a conference in Dubai coming up, not too distant future, one after that in Europe, Australia, and the United States. These conferences are there to support you as a vibration analyst. Yes, the training courses are great, and yes, there are free videos, a lot from us, but these conferences are a chance to meet other people just like you, to talk to them about what they've learned from vibration analysis, how they solved problems and so on, but also to listen to presentations, case studies, great new technologies that are coming out. There's social events, there's great exhibition and so on. So we need your support because we're putting on these conferences to support you. And at the conference in Dubai, well actually before I say that, we are offering a 10% discount to anyone watching this webinar. All you got to do is register with the code IMVAC, International Machinery Vibration Analysis Conference. IMVAC, you do that, 10% discount. And if there's a few of you at your site that are involved with vibration analysis, well, if you register 2 people, a third person can come for free. So what I was about to say is that I will be delivering a few presentations there, but also 2 half-day workshops. One talking much more about how you detect rolling element bearing faults, lots of examples and all of that, but also talking about how you prevent the faults in the first place. What are all the causes of the faults, and therefore how do you prevent them? And then in a second half-day workshop, going into much more detail about the proximity probes, the key phase of the orbit plots, the centerline plots, the Bode plots, full spectrum, and so on. And if you were thinking about going into category 4, that would be a good workshop to attend, and maybe you can see how you feel about the topic afterwards and whether you're ready for a category 4. So I really hope you enjoyed this presentation. I hope you learned something from it, but I also hope to see you at the next IMVAC conference.